This is lecture video 51, and in this lecture we try to understand how to apply partial fractions method when the denominator contains quadratic factors. Okay, what's a quadratic factor? It is a factor of degree 2 which is irreducible. Okay, so if you have a polynomial of degree 2 like this, where the discriminant is where the discriminant is less than 0, meaning that this factor is irreducible, you cannot decompose it into its linear factors anymore, then you will call it as a quadratic factor. Okay, discriminant being b squared minus 4ac. If this expression discriminant is less than 0, then this degree 2 polynomial cannot be reducible, cannot be decomposed into its linear factor, so you need to leave it as it is. It's a polynomial of degree 2, so we call it as a quadratic factor. And for quadratic factors, you write not just a constant a, but ax plus b form in the nominator part. So you can maybe make sense of it, like you always write one less degree to the denominator by applying partial fractions technique. So x plus 2, the other factor is linear of degree 1. So you write one less degree. This is constant. Constant has degree 0 as a polynomial. So here the degree is 2 and you write one less degree. One less degree. So degree 2, you should be writing some form of degree 1. That's why it is ax plus b. Okay, then what if denominator contains repeated repeated quadratic factors? So x squared plus x plus 1 is a quadratic factor and it is repeated. It repeats itself 2 times. So we covered what we should do for the repeated factors. You keep writing it over and over again till you reach the exact power given in the original denominator, right? That's why write it one more time. So you reach the exact power, which is 2, then you stop. And you also need to write ax plus b and cx plus d to the denominators. This is the rule for what you should write on the nominator for quadratic factors. You still need to obey that rule, okay? And for the quadratic factor, this is the for the linear factor, you write constant as usual, okay? So this is your quadratic factor. It is repeated like this, and you write ax plus b forms over it for the quadratic factors, okay? So now let's exercise this technique, make some practice on this technique in the following question. Okay, look at the denominator, please. As you can see, we have a quadratic factor here, okay? Because you cannot decompose it anymore, discriminant is negative. Okay, so this is a quadratic factor. And what about the other expression, other term? So this is a linear factor which is repeated 2 times. Okay, we have a quadratic factor and here we have a repeated linear factor. So you need to understand the difference between these. So this cannot be decomposed anymore. It is irreducible. And the next term, which is x minus 1 2 square, it is a repeated linear factor. Okay, so we know what to do for the quadratic factors and for the repeated linear factors. Okay, let's handle the quadratic factor part first. Ax plus b form should be written for that. And this is repeated linear. You keep writing it over and over again till you reach the exact power, which is 2 here. Okay, so let me write down the details. This is a quadratic factor and This one is a repeated linear one. Okay, so this is the partial fraction decomposition of it. And now we need to expand to find the coefficients A, B, C, D. Okay, this should be expanded by this one. This is missing there, and x squared plus 1 is missing to obtain this common denominator. These two are missing. And for this one here, x squared plus 1 is missing. Okay, if you do the expansions, ax plus b is multiplied with this thing, c is multiplied with these two, and d is multiplied with this. And then if you do the multiplications here, and then you can just rearrange the terms like x cubed, x squared, x, and the constant term. If you do this rearrangement in terms of x cubed, x squared, x, and constant term, then you can compare the coefficients of the same degree terms, right? On the left-hand side, we have no x cubed, we have no x squared, you see? That's why the coefficient of x cubed should be 0, no x cubed on the left. The coefficient of x squared should be 0, because there is no x squared on the left. And the rest is -2 is the coefficient of x on the left. That's why this coefficient should be -2. And +4 is the constant term, which means that this constant term on the right should be +4. Okay, like this. -2 should be this part, and +4 should be the constant term on the right. And after solving this system, you can obtain the unknown coefficients. Okay, the coefficients are solved as, after solving the system, A is 2, C is solved as -2. From here, you see that B is solved as 1, and D is also 1, okay? I won't go into details about how to solve this system. You can just try to eliminate variables till you solve each of them. Okay, next. Next is the integral part. We were trying to handle this integration, which is -2x plus 4 divided by this quadratic factor and a repeated linear factor, which is this one. Okay, so what we obtain? We obtain that. Now I am trying to eliminate the integrate from the right-hand side, from the partial fraction decomposition of it. So this was the structure, x squared plus 1 plus c over x minus 1 plus d over, as it is the repeated linear factor, like this. And we solved all the coefficients. A is solved as 2, B is 1, C is -2, and D is 1. Now I think we are ready to integrate it. Okay, let's rewrite with the values of the coefficients. We have this plus the integral of -2x minus 1, and then 1 over x minus 1 squared dx. So look at the first integral, please. Sorry. Okay, this one. How to integrate it? You can try to use a substitution first, but it won't work. Let me show you why it is not working. You see, if this +1 wouldn't be here, then you would call denominator as du, denominator is u, and you know how to integrate du over u. It is ln u, right? But with this +1 here, this substitution is not working anymore. That's why you can consider now to divide this rational function into 2 parts without writing a common denominator, but writing it separately like this. Then your substitution will work, okay? So Then if this is u, this is exactly du, and you integrate it as ln absolute sine of u, where u is x squared plus 1, okay? So how do you integrate this? This is a very famous rule. It is a rule. 1 over x squared plus 1 is derivative of some function. So it is the derivative of the arctangent function, if you remember, arctangent x. And now this one is integrated as -2 goes out. The x over x plus 1 is obviously ln of this. And the last one is integrated as, so you can understand it if you write it like, sorry, let's call it first. Let's use a substitution first, x minus 1 squared dx. If you choose this substitution u, then this part is exactly du. Then you understand that it is in fact in this form, right? So evaluating the integral is easy. Add 1 to the power, divide by the same power, then do your back substitution. That's why this last integral is 1 over x minus 1. And then you add your arbitrary constant c, of course, because you are dealing with an indefinite integral. Okay, like this. So we handled the case where the denominator contains a quadratic factor and a repeated linear factor, okay? This is quadratic because it cannot be decomposed anymore, as the discriminant is less than 0. Okay, let's do this last case where we have a repeated quadratic factor, okay? This is repeated and at the same time quadratic. Quadratic factor, what about this one? It's a linear factor, right? Just x. Remember, the general form of linear factors is in this form, ax plus b. If you choose a as 1, b is 0, you just obtain x, right? So x is a linear factor for us. And let's also emphasize that this is repeated. So your quotient, your rational function, can be decomposed like this, where you have this linear factor. That's why you just insert a constant over it, and you have this quadratic factor. You keep writing it over and over again till you reach the exact power here, and then you know what to write over quadratic factors. You need to write 1 less degree bx plus c dx plus e. Okay, like this, and then you need to expand. This should be expanded by the missing part, this part, and do the same for the other terms. This should be expanded by 1 more of this and then x. This should be expanded by x. So do all those expansions. A is multiplied with this expanded factor. This part is multiplied x times x plus 1. Bx plus c is multiplied by, yes, sorry, I forgot this, x squared plus 1 times x, and this is multiplied, expanded by x. So you do all these multiplications, and then after doing the multiplications, you need to rearrange the terms in terms of x to the power 4, x cubed, x squared, and the constant x squared, x and constant term. And look at the left-hand side. There is no x cubed on the left. There is no, let's start with x to the power 4. No x to the power 4, no x cubed, no x squared, and no x. Which means that all the coefficients of x to the power 4, x cubed, x squared, and x should be all 0. Because we are just comparing the coefficients on the left-hand side and the coefficients on the right-hand side. And the constant term should be the constant term on the left, which is 1. Okay, a plus b is 0, c is 0. this is 0, the coefficient of x, there is no x on the left, should be 0. Constant term is 1, constant term on the right should be 1. Okay, and then you can easily solve this system. C is already 0. A is 1. If A is 1, then you solve B as -1, right? B is -1. B is -1. A is solved as 1. That's why D should be -1 here. And since C is 0, E should be 0 too. Okay, now we know all the coefficients. Then I am ready to integrate the given example. The example was like that. X squared plus 1, which is a quadratic factor, it is repeated. So I will handle this integration on the right-hand side. A is solved as 1, right? Okay, let me just write the whole thing, then I will insert all the coefficients. Bx plus c, x squared plus 1, okay. And then the last term, dx plus e over x squared plus 1 squared. So, like that. Let me just write it inside one integral so that I can put 1 dx at the end. Okay, I solved A as 1. I solved B as -1, C as 0, D as -1, E is also 0. So what do I have inside the integrals? A is 1. This is dx over x plus minus x over x squared plus 1 dx plus minus x over x squared plus 1, x over 2. This is what we have to integrate. Okay, let's start integrating. This is integrated as ln, and this is integrated as, if you call this part as u, this part is du over 2, okay? And then you need to integrate it. There is this minus, be careful, -1 over 2 goes out. Du over u is integrated as absolute sine of u. And this part is integrated as, if you call this part as u, similarly, this is again du over 2. So what you have for this integral with this substitution, you have du over u squared. How do you integrate it? 1 over 2. So this is in fact u to the power -2 du, right? And this is a power function, and you know how to integrate it. -1 over 2, add 1 to the power, divide by the same power. So -1, that's why the result is just 1 over 2 times 1 over u, I guess, where u being this expression. And then at the end, please don't forget to put this arbitrary constant c, because this is, all those are indefinite integrals. Okay, that's it. In the last question, we handle the case where we have repeated quadratic factors, so that you write this structure over and over again till you reach the exact power, and you obey the rule about what to write on the nominator, like bx plus c, dx plus e. That's it.